It's number 4.
Okay. All right, good morning. So let me recall what our setting is. So we have a probability measure space, an ergodic transformation, and a measurable bounded function from omega to r. And then we set v omega, omega and n in z to be ft to the n omega. Okay, so this is ergodic with measurable bounded sampling function f. And so we use these sequences as potentials, and so h omega is a discrete Schrödinger operator in one dimension for the most part, and so whenever things extend to higher dimensions I'll try to remember to point it out. So this is how it acts on L2 of z. And so yesterday we showed that there is a non-random spectrum and non-random AC, SC, and PP spectra. So sigma AC, sigma SC, sigma PP of h omega are mu almost everywhere constant or independent of omega. So that's what we discussed yesterday. So today I want to introduce two quantities that are associated with these operators in this very general context. The density of states measure and Lyapunov exponents. Talk about a connection between the two expressed through the Thouless formula, and if there's time remaining, explain how they relate to spectral questions about spectra and these spectral parts. So let me define the density of states measure. So it's a measure on R, and in fact it will turn out it will be a measure supported on, I should have actually recalled the notation, so given by these sets. Okay, so these are non-random sets, so that, for example, sigma of h omega is equal to capital sigma for mu almost every omega. Okay, so this measure, let's denote it by dk. So we have to say how it integrates functions. And so if we define this for sufficiently many functions, it determines a measure. Okay, so how do we want to define that? So you can, you have this functional calculus because the h omegas are self-adjoint, so you can form this new operator. So you can think of G as bounded measurable, for example, or continuous, doesn't matter. So then we apply this new operator to delta 0, the vector in L2, and then take the inner product in L2 with delta 0. And then we integrate against mu. So I denoted that by expectation yesterday. I will still do this, but just to... so this is the expectation of this inner product. So, and just to emphasize what you actually get here, let's recall what the spectral theorem actually says. The spectral theorem says that with the spectral measure associated with the operator h omega and the vector delta 0, this actually is equal to the integral of g against this measure. So let's denote it by nu h omega delta naught. So this here is the spectral measure corresponding to this pair. And the spectral theorem says that this funny inner product is equal to this integral of g. So if you now compare the two sides, you see that this measure is nothing but the mu average of these spectral measures. Okay? So that's what it is by definition. So this defines the so-called density of states measure. Okay, so just to clarify terminology, sometimes people call it density of states. So let me tell you what I call the density of states. So the distribution function of this measure, So if you integrate the characteristic function from negative infinity to e against dk, right? So that's the distribution function of the measure. That I call the integrated density of states. And so this may or may not be an absolutely continuous measure. It really sometimes isn't. But if it is, it has a lot of Nikodym derivative. And so that density then I will call the density of states. Okay, so if the density of states measure is absolutely continuous, then its Radon-Nikodym derivative with respect to Lebesgue measure will be the density of states. Anyway, so these are the two notions that I will talk about. Okay, so the first observation is the following. So the almost sure spectrum is the topological support of this measure. Okay, so the measure actually supported on the spectrum, so it gives no weight to the complement of the almost sure spectrum, and moreover, the spectrum is the smallest closed set with that property. Okay, so I think I will sketch the proof at the risk of running out of time again before I cover all the things that other people need me to cover. But, well, every now and then I will give some short proofs. Good, so this, okay, so to paraphrase someone who spoke earlier, if you are talking about equalities, you're really talking about two inclusions, right? So let's see how we can prove these inclusions. So maybe the easier one, let's see, which one is easier? Probably this one. Okay, so we want to show that the support of dk is contained in the in the almost sure spectrum. So suppose we're not in here, and then we want to show we're not in there. Suppose E is not in the almost sure spectrum. Okay, but the almost sure spectrum is a closed set. Okay, so then we can actually take a small open interval, well, a small interval around this that also doesn't intersect the spectrum. Okay, so let's see. So I take the small interval, and this will not intersect the spectrum. So the spectrum is here. Okay, and then I want to take a function g that's non-negative. It's 1 at e, and it's supported in the small interval. So it's supported in the complement of sigma. Okay, so this will be g. So g is non-negative. G at e is 1, and g restricted to sigma is identically 0. Okay, so it's possible to find that because sigma is closed. All right. So sigma is the almost sure spectrum. So this means that sigma restricted to the spectrum of h omega is identically equal to 0 for almost every omega, right? Okay, but that means that g applied to h omega is equal to 0 for almost every omega, right? So a function applied to a self-adjoint operator, the outcome only depends on the values of the function on the spectrum. And so if it happens to be 0, you get 0. So the 0 operator. So that's 0. So that implies now that this here is 0. So now I will write expectation again. H omega g. Okay, so here this guy is 0 for almost every omega. So therefore this inner product is 0 for almost every omega, and integrating against the mu gives me 0. So this is 0, but by definition it's g dk. Okay, but g is non-negative, and it's 1 at e. Sorry, g continuous. Okay, so the point is that it's actually bounded strictly away from 0 on some intervals, on some subinterval. And so now, with these conditions here, you see that E is not in the support of the measure. So this implies that E is not in the support of dk. Okay, so the other inclusion is proved in a similar way. So suppose E is not in the support of dk. So then, no. So before we assume that it's not in sigma, right? And so I'm showing that sigma is contained in the support of dk, and I'm proving that by assuming that I'm not on the right-hand side and show that I'm not on the left-hand side, right? So so let me just see. Okay. Okay. So then we take a similar function g. So find g continuous, so that g at E is 1, g restricted to the support of dk is 0, and non-negative. Same condition as before. Okay, so so there exists such a g. Because I'm talking about the topological support of the measure which is closed, and again, once you're closed, if you're in the complement, you can find an interval about your point, and on that interval you can choose such a function g as in the picture up there. Okay, so once I have such a g, by these conditions, g dk integrate, so that integral is 0. Okay, by choice of g. So by definition of my density of states measure, this is equal to the expectation of this inner product. Okay, so that's by definition. But now I use something that I should have recalled here. So the crucial identity that we used a few times yesterday is that if I conjugate h omega with this unitary shift operator on L2, I get ht omega. So this was a boxed equation yesterday. It will be a boxed equation again. Okay. So of course, h omega and the one with the shifted potential are unitarily equivalent by the shift, and it's expressed by this identity. And I want to use, so as soon as you have that, it extends to functions of the operator. So I want to use that here. So, right, so so I want to do this n times. So h omega, so maybe the star goes here now. Right. So to minus n g t to the n omega u n delta naught, and like this. Okay, so that's good. So that's by this boxed equation. And now I bring u to the n to the other side, and then note that I get delta n, or minus n. That I will never get right, so it's either n or minus n. Okay, because I shift n times, so I go from 0 to n. And now, so when I said that the system is ergodic, there are really two assumptions about the interplay between t and mu, namely mu is t invariant, and also t invariant functions are almost surely constant. Those are the two things that we assume. And so here we just use the invariance. So this e is integration against mu, but we can just get rid of this t to the n here because mu is t invariant. And so we get delta n g h omega delta n. Okay, great. So now because g is non-negative, this will be a non-negative operator here. So the integrand is non-negative, and so the integral is 0, and therefore the integrand is almost everywhere 0, and this is for each fixed n. So for every n in z and mu almost every omega, I have delta n g delta n equal to 0. Okay, so because the integrand is non-negative. And now, so this exceptional zero measure set depends on n, but there are countably many of them. I intersect them. I take the union of the exceptional sets. It still has zero measures. So for mu, almost every omega, and then for every n, I have the same thing. Okay? And so this tells me the following. So this is a non-negative function, and here really I view this as the integral of g against the spectral measure corresponding to h omega and delta n. Okay, so g is a non-negative function. It's 1 at e, and it's positive in the neighborhood of e. But the outcome is 0, so therefore I'm away from the support of this measure. So this implies, so actually I can just do this in one step. So E is not in the support, the topological support of d nu h omega delta n. Okay, and so now the delta n's form a basis, and therefore the union of the supports of their spectral measure cover the entire spectrum. And so therefore, for mu almost every omega, E is not in the spectrum of h omega. Okay. So you don't even need all the delta n's, but you get it for all delta n's, and that's more than enough to ensure that you're not in the spectrum of the operator. And so this is it. So almost surely you're not in the spectrum of the operator, so therefore you're not in the almost sure spectrum. Okay, so that was the one proof that I wanted to do in detail today. Where's the... So now, if you want to take this a little bit further, you need more general properties of ergodic transformations. Namely, you need ergodic theorems. So let me recall the additive and the subadditive ergodic theorem. So the additive ergodic theorem is Birkhoff's pointwise ergodic theorem. So again, the setting is that I have this ergodic triple omega mu t, and then I use, let me just use f again. So in these general theorems, f will just be some function, not my specific sampling function, just some function. So f in L1 omega d mu. And so what we want to compare are time averages and space averages. Space averages given by integration against d mu. What are time averages? Time averages is you start somewhere and then you follow the trajectory of that point under t, and then you just average whatever you see sampled with f over time. So this is what you do. So you follow the trajectory of some point omega. You sample with f, okay? So this should be a real valued function, for example. And so now we average. So we take this from 0 to n minus 1. And here's my Suzawa average of the first capital N sampled points. And so this now converges as n goes to infinity. So this is a time average now as n goes to infinity to space average, namely the integral of f. Okay, so the integral of f against d mu, and so this holds for mu almost every omega. So this is why it's a pointwise statement, because it really holds in the sense of pointwise convergence almost everywhere. So this is the additive version. Why additive? Well, because these sums here are additive, right? If I sum from 0 to some larger number, I can view that sum, if I partition the large time interval into 2, as a sum of 2 such sums, okay? So that's why it's an additive quantity that one looks at. Kingman looks at subadditive objects. So here you have fn's that are integrable. So here we will actually, for simplicity, there is a more general version which we won't need, assume that the L infinity norm is bounded by some uniform constant times n. Okay, so now if I want to express a subadditivity condition, So again, so before I said that, well, if you go up to n, and then maybe n plus m, then you can really view the sum as a sum up to m plus the sum of length m that starts at this point. Okay, so right, if you look at the sum from 0 up to n plus m minus 1, you can view it as the sum up to n minus 1, and then a similar sum that has m terms but starts at the shifted point. So if I want to turn this into something that only satisfies a subadditive condition, so now I'm looking at something of length n plus m, and again I want to compare it against sort of the division into two pieces. So let's see, so I want to look at the first n steps, and then I want to look at the next m steps. But of course, now that I've already walked n steps, I have to look at t to the n omega. So now I have these two numbers, and the question is, how does this number relate to those? And subadditivity means exactly this, subadditivity condition.
If you really want the infinity norm, I'm pretty sure it's true with an L1 norm.
Yes, but we have it.
It's for the example you want, you have
Right.
it, but you don't need it.
Okay,
L1
so
is enough for king.
okay, yes, okay, fine. So yeah, but we have bounded potentials, and so it will be, yeah. So just for simplicity. Okay, so then so it's again a question about convergence. So 1 over n f n omega, okay, again converges now as n goes to infinity to some limit. Again, mu almost everywhere. And moreover, so this is why I want this, the limit is finite, and f star is actually equal to the inf of 1 over n, the integral of fn. Okay, so that's what Kingman says. And well, the first application of Birkhoff's ergodic theorem is to the density of states measure. Namely, there's a different way of viewing it that's maybe more attractive even. But for proving this theorem, the other definition was more convenient. But okay, so there are two statements. So one is K, the integrated density of states, is continuous. So here this is initially a one-dimensional result. So I should have said that. So what I did before really had nothing to do with one dimension, so that is just a general higher dimensional thing. But yesterday I pointed out that, well anyway, that the solution space for fixed energy of the difference equation is just two-dimensional in one dimension. And so that implies, for example, that the almost pure spectrum has no isolated points, and the same argument also implies that the integrated density of states has no jumps, or the density of states measure has no atoms. And B, the measures d, k, omega, n defined by, well, I'll say how in a second, converge weakly to dk. Okay, so how are these measures defined? So you take, by placing mass 1 over n at each of the eigenvalues of h omega n, which is just the following thing. So you cut out the n by n matrix of this form. So it's just the restriction of h omega to the interval 1n with Dirichlet boundary conditions. So this well, has n distinct real eigenvalues. At each of them you place mass 1 over n, that gives you a probability measure. That probability measure you call dk omega n, and almost surely. Okay, and then for mu almost every omega, these measures will converge weakly to the density of states measure. So in this sense, the density of states measure really is sort of the infinite volume limit of what you see for the finite volume restrictions of your operator, almost surely. Okay, so again, I will try not to run out of time. So both these things are not difficult to prove, but I probably won't have the time to discuss that now. And Birkhoff's theorem is important there. Okay, so now I will move on to the definition of the Lyapunov exponent, which is the other important quantity that you always have in the general setting. And the Lyapunov exponent is, at least the way we introduce it here, a strictly one-dimensional object. Okay, so the density of states measure is not. So the Lyapunov exponent. Okay, so we look at the difference equation that has been mentioned a few times. So really it's the generalized eigenvalue equation for H omega. Okay, so you take some either real or complex E and then you fix it. You fix your omega and then you look for solutions U that you don't require to be L2, just general solutions of the difference equation. Yes, thank you. Okay, so the Lyapunov exponent tries to measure the average rate of exponential growth of these solutions. And so how does it do that? Well, you express solutions via transfer matrices. So you rewrite this as follows. So if you want to relate un plus 1 and un to un and un minus 1, well, you just look at the equation. So first of all, here, obviously, you have that. But here, you just bring these two terms to the other side, and then you express un plus 1 in terms of a linear combination of these two things. And the coefficients are as follows. Okay. So that's just rewriting the equation in matrix form. But then you can iterate that. Okay, so you can apply the same argument to this vector to bring it down to n minus 1, n minus 2, and then you do it all the way to u1 and u0, right? And you need to do it n times, and all these matrices are of the same form. The only thing that changes is the index c and the potential term. So they are n terms. Okay, so this tells you that if you want to study sort of the large n behavior of these solutions, well, you have to look at your initial vector, but then you apply these matrices. And so there will be some notation. So A, E, N, omega. All right. So remember that our F is bounded, so therefore V is bounded. And for fixed E, these matrices are uniformly bounded in omega, and therefore the products have a uniform exponential upper bound, and therefore the following thing here, if I take the log is one that satisfies this assumption here. And also by submultiplicativity of the norm, which turns into subadditivity for the log of the norm, I have this subadditivity condition here. Okay? Apply Kingman. And so what we get is there exists L of E, which is the limit as n goes to infinity. No 1 over n. The 1 over n comes in here, right? So with the 1 over n, it's not subadditive. This is subadditive, sorry. So the limit is of 1 over n times this function fn. Okay? And that is also equal to the inf of the n's of 1 over n expectation of log of this matrix norm. Okay, so that limit exists, and we'll call it L of E because obviously it depends on E. And so here it's actually useful to just do it for general complex E. Right. Nevertheless, the determinant of such a matrix is 1, and so therefore the product has determinant 1. And therefore, its norm is at least 1, and so the log is at least 0. And so whatever these things do, if they have a limit, the limit must be greater than or equal to 0. Okay? So this guy is called the Lyapunov exponent. So either L of E or the function of E is called the Lyapunov exponent. L is the Lyapunov exponent. Okay, and so you see here, first of all, that L of E measures the sorry about him being precise. So Kingman tells you that's for almost every omega. So this measures either the average or typical rate of exponential growth of these norms. And so then the idea, of course, is if you have exponentially growing norms, then for suitable choice of initial conditions, you will have exponentially growing solutions at that same rate. And actually, if you have such a situation, you typically, well, also have exponentially decaying solutions. So I will, if there's time at the end, try to explain a little bit how this, if L of E is positive, actually does try to indicate that we're relatively close to a localized situation. Okay, but anyway, this is initially just a definition. And there are also some basic properties of the Lyapunov exponent that I'll try to list and partly make plausible. So the first okay, so theorem. Well, the Lyapunov exponent, so the function L from C to 0 infinity is subharmonic. That is, it has two properties. It's submean and it's upper semi-continuous. So submean and upper semi-continuous. So submean, so well, means that if you look at L at some E and compare that with the values of L on some circle centered at E, okay, so R is positive and phi will run from 0 to 2 pi, and so let's average. I'm sorry. Okay, so now I'm trying to compare the value at the center with the average over the circle centered at that point. And submean it means that I have an inequality of this form for every E and every positive R. Upper semi-continuous is an inequality in the other direction. So if I look at L of E and compare that with L at points that approximate E, then I'm bigger than the lim sup of these guys. So L E n if E n converges to E. Okay, so I really have inequalities that go in opposite directions, and combining that, so this has the consequence that if I look at L of E and compare that with the following average, pi r squared, and so now I really want to average over the ball centered at E of radius r, L E prime, and now two-dimensional Lebesgue measure. Okay, so I just average over the whole disk the thing. And so now I get one inequality by viewing the disk as a bunch of circles that shrink down to radius 0. And on the other hand, I also have the inequality in the other direction that holds along all possible subsequences. And so actually here I get an equality. So this actually follows from quite general properties. So if you look at L of E being equal to this inf, so you work your way inside out basically. So this A and omega depends on E analytically. Okay, and then you take log of norm of that, and that by general results is a subharmonic function, and then you can work your way out. Then you look at this mu average and the inf of 1 over n times that, and sorry, the 1 over n you bring in here. And so the expectation and the inf preserve the subharmonicity. So this result follows sort of general principles.
Should there be a limit quick to see?
Yes, absolutely. Sorry. There should also be, no, yeah, that's right. There should just be a limit. Absolutely. Sorry. Okay, less confused now? Okay, right. So I wanted to point this out because this really is behind a simple proof of the Fowler's formula, which links the two quantities that we just introduced. So for every E in C, I have that L of E is equal to the integral of log absolute E minus E prime dk E prime. Okay, so, well, okay, so let's sketch. So prove this first. For E not real. Okay. Why? Well, if E is not real, then this function of E prime is a bounded continuous function. So it's nice. And then we know that this measure dk is approximated weakly by these measures dk omega n, right, that were obtained by placing masses 1 over n on the eigenvalues of the finite volume restrictions. Okay. So actually, let me copy the formula to make this. There you go. So I'll put this here. So this is a formula that's useful, and once you see it, relatively easy to check. So A n omega E actually is equal to the following. That E minus H omega n, that E minus H n minus 1 T omega, that E minus H omega n minus 1, and minus that E minus H T omega n minus 2. Okay, so how do we check this formula? Well, we look at the definition here, right? So, for example, so A n E omega maps this guy to that guy. So on the other hand, suppose this vector here is 1, 0. Okay? If I use 1, 0 for U1, U0, then I just get the first column of this matrix. Okay, so we will get this column of this matrix. Okay, so now this is a vector that starts off as 0 here, and 1 here. And then I inspect what it does at n and n plus 1. And so this guy here, which is the top left entry now of this matrix, is 0 if and only if this guy is 0. But this guy is 0 if and only if the solution that starts out with 0 here is a true eigenvector for the Dirichlet problem on the interval 1n. Okay? Just because it satisfies the Dirichlet condition here, and it satisfies it at n if and only if this entry is 0. Okay? But this entry is this thing here. So this thing here is 0 if and only if I'm an eigenvalue of the Dirichlet problem on the interval 1n, which is exactly this operator here. Okay? Moreover, by definition of this matrix, if you just look at the upper left corner of this product of n things, is a monic polynomial of degree n. Okay? So therefore, it has the same zeros as this polynomial, and this also is a monic polynomial, so they're equal. And the same argument you can apply to the other 4 entries. So once you view these transfer matrices in terms of these determinants, or Dirichlet determinants, then the eigenvalues enter, because of course this determinant here is given by the product of E minus the eigenvalues of this operator, right? So, good. So, so for E, you take the log of the norm, and so of course all norms are equivalent. I can take the max of the entries, for example. So I can look at individual entries, and when I look at individual entries, then I really get the log of the absolute value of these determinants, which are products of E minus eigenvalue, and so I get a sum of logs of E minus eigenvalue, and which is exactly this integral for the finite volume approximation. Okay, and because I have a bounded continuous function for non-real E here, the weak convergence statement that we had before will tell me that as I now send n to infinity, the eigenvalue expressions will converge to this, and the other thing by Kingman converges to that, and it's equal. Okay, so using the formula on the left, this formula, and weak convergence, all right, and then deduce it for E in R using the formula there, namely this one. Okay, so if you look at this formula here, you see I have 2 subharmonic functions, so this by the result and this by definition basically, that coincide off the real axis. Okay, but then when I integrate against 2-dimensional Lebesgue measure, I can just ignore the real E's, and I have coincidence on all the other E's, so the 2 sides are equal, and therefore the limits are equal. So this actually is almost a complete proof. All right, so the Fowler's formula initially just is interesting because it relates these 2 concepts, but of course it is interesting also for other reasons, some of which will be explained by Barry. So nice application, but I won't introduce the necessary terminology. If L vanishes on the spectrum, then dk is the equilibrium measure associated with sigma. Okay, so I guess you will talk about this. So it sounded like that yesterday. So I will not define.
Tell people what equilibrium is.
No, that's why I'm saying I'm not defining it now because I'm assuming you will. And so this is interesting. So first of all, there are many models of interest where the Lyapunov exponent vanishes. I mean, so periodic, for example, but maybe that's not so exciting. But then finite gap quasi-periodic, and many of these subshift models that I don't discuss, but could have. So there are interesting classes of operators in this context where this applies. And then this...
Almost Matthew below the critical color.
Yes, that too, that's right. And so it says that the density of states measure really is intrinsically defined in terms of the spectrum. You don't actually need to know the operator anymore. You can just read it off from the spectrum. This notion of equilibrium measure just needs to know what the set is. Okay? In other words, among those that are isospectral and that have vanishing Lyapunov exponents, they must automatically have the same density of states measure, for example. Okay, so that's the Faldus formula. And so now let me spend the remaining time on, well, maybe this here. So the idea really is that the Lyapunov exponent can either be 0 or be strictly positive, and you somehow want to distinguish these two cases and hopefully deduce two different conclusions from it. And in fact, it's beneficial to subdivide the region of positive Lyapunov exponents one more time. So we want to consider energies where the Lyapunov exponent is not only positive, but we have more. This convergence is not pointwise almost everywhere, but in fact it's everywhere and uniform. Okay, so let UH for uniformly hyperbolic. So let me just define it for R, because ultimately we would like to understand these sets sigma, sigma pp, sigma AC, which are all subsets of R. So where there exists C greater than 0, lambda greater than 1, so that for all omega and n in Z, we have norm of A, E, n omega, it's greater than or equal C lambda to the absolute n. Okay, so so this definition is basically what I said before, just a little bit weaker, but basically it captures. So I have a uniform exponential lower bound for the growth of these matrices, for the growth of the norms of these matrices. Okay, so some people like to call this behavior uniformly hyperbolic, and the set UH is a set of energies where these matrices behave in a uniformly hyperbolic way. Okay, so then there's a theorem which says that, okay, so let's see. So let me make my life easy. So suppose T is minimal. So you can relax that, but so minimality was introduced yesterday. All orbits are dense. That holds for irrational rotations of the circle. It holds for suitable, well, minimal shifts of tori, almost periodic transformations, and it holds for the skew shift. It doesn't hold for these shifts leading to random models. So, and then the set sigma is the complement of UH. Okay, so UH captures precisely the resolvent set, the almost sure resolvent set. I mean, in fact, it always includes all resolvent sets, and sometimes more, but if you're minimal, it's precisely that. Okay, so this is nice because basically, because you're interested in the spectrum and the spectral parts, you have to look in the complement of uniform hyperbolicity, and this complement now you subdivide further. So Z are the energies in R, so that L of E is 0, and NUH for non-uniformly hyperbolic, well, it's basically everything else. So it's R minus Z union UH. Okay, so those are the energies where the Lyapunov exponent is positive, and yet you don't have this uniform exponential lower bound. Okay, good. So Well, so this partitions the real line consisting of all real energies into three parts, Z, NUH, and UH. At least under minimality assumptions, you know that the spectrum really is the union of Z and NUH. And so here's the thing. You try, I mean, this is to a certain extent wishful thinking, but it's at least a guideline. You try to identify or put in correspondence Z and sigma AC and NUH with sigma PP. Okay, so it's wishful thinking because in this expected, maybe generic or whatever typical picture, sigma SC doesn't figure, and of course sometimes it's there. And so the truth of the matter is that you can have singular continuous spectrum both here and here. So in general, this just isn't true, but basically, well, on the one hand, you have one general result by Ishii, Pasteur, Kotani that expresses the first statement in a suitable form that actually is true. This one here. But I'm not naming names, I'm sorry, so I shouldn't have said that. So sigma AC is the essential closure of Z, okay? So which is the set of E's, so that for every epsilon greater than 0, the Lebesgue measure of Z intersected with the ball centered at E of radius epsilon is positive. Okay, so this is by definition the essential closure. So you see here if the set Z is reasonable, so for example consists of intervals, then then even more is true. But if not too much of Z disappears in the essential closure, it does generate sigma AC. Okay, but again, it should be pointed out that the essential closure of a set is empty if and only if the set has zero measure. And there are many interesting cases where the spectrum sigma is equal to Z and yet has zero measure. So those are cases where sigma AC is empty and yet all the Lyapunov exponents vanish on the spectrum, and therefore actually it will be purely singular continuous. But those are in some sense cases that, while they do exist, don't really deter too much from the fact that you do want to associate AC spectrum with zero exponents. So this is a theorem that holds in complete generality in this one-dimensional general ergodic Schrödinger operator context. So the other thing is, going from positive exponent to, localization. Okay, so this is of course something where a lot can be said. But, so what I'm really trying to convey here is that if you are dealing with some given ergodic family of Schrödinger operators, you probably do want to identify the spectrum, and then you do want to study the Lyapunov exponent and ask whether it's positive or zero. That should probably be the first thing you do. Okay, and once you do that, say you understand the spectrum and you understand where it's zero, then you apply that theorem. That gives you some statement. Suppose you find that the Lyapunov exponents are positive for many energies in the spectrum. Then what? So this is what I'm saying here. The first inclination should be to try to prove that you're localized in that energy region. Okay. So again, word of warning, it's just not always true. So for example, yesterday the almost Mathieu was mentioned. So let me recall that there was this all these three different cases in the supercritical situation. Okay. So here, it's actually true that for every E in the almost sure spectrum, which depends on lambda and alpha, but not on theta, by minimality, it's true that L of E is equal to the max of 0 and log lambda. So in other words, you understand the Lyapunov exponent entirely on the spectrum. You know exactly what it is. So up to lambda equal to 1, it's just 0. And above 1, it's positive, and it's equal to log lambda. And yet, you can't always go from this positivity statement to localization. So remember that for lambda greater than 1 and generic alpha, all theta, or all alpha and generic, all generic theta. And generic means dense G delta set of thetas or alphas. There are no eigenvalues. So in fact, the spectrum there is, the AC spectrum is empty by that statement. And there are no eigenvalues, so it's purely singular continuous. Okay, so here's a situation where you have positive exponents throughout the spectrum, and yet there are absolutely no eigenvalues. Okay, so it just doesn't hold in general, and yet you still try to ask, because it's just most of the time it's true. This is sort of, it's an exceptional case, but it's in some sense really most of the time true that if you observe positive exponents, then you do have a localized system. Okay, so how does one do that? So maybe I have 2 more minutes. Okay. So again, so the first thing is to recall something I said on Monday, existence of generalized eigenfunctions. Okay, so spectrally also for mu, h, omega, and then whatever vector, psi, almost every e, there exists u, a solution that's polynomially bounded. Well, doesn't matter. Okay, so this is what you always have. This is just true for general Schrödinger operators. Doesn't even need the ergodicity context. So you do that, and so then the goal is to show that any such generalized eigenfunction actually must decay exponentially. If you can do that, then you get localization, because you cover spectrally almost every energy. But if it's true that for spectrally almost every energy you have an exponentially decaying solution, well, that certainly is an eigenfunction, then spectrally almost every energy is an eigenvalue, and you have your point spectrum, and the eigenfunctions are exponentially decaying. Okay, so the goal is to use to prove that every generalized eigenfunction decays exponentially. Okay, that's good. And so here's how you would try to do that. There's a Poisson formula. Okay, so you look at finite intervals, and you look at solutions of your equation, and then what you can do is you can relate the value at some interior point to the values at the boundary here. So u at, say, a minus 1 and u at b plus 1. So you're looking at the interval ab, and you can relate this to, well, you can express it in terms of a linear combination of these guys where the coefficients are given by, well, let me write it, g, e, well, I don't know. So what I want to put here is the following. I want to consider Green's function entries. So Green's function, so I want to look at h restricted to ab, say omega, the restriction is here, omega, and then minus e inverse, and then, well, I look at these guys. Well, maybe. Okay, so here are the matrix entry of the resolvent of the finite volume restriction, yes, of your operator. And so the point is that if you could show that these guys are exponentially small in the distance between these 2 points, then for n's that are sufficiently far away from the boundary points, so the things that go here are exactly these guys coupling these 2 points. Okay, so for n's far away from the boundary, if you can show that these guys are exponentially small in terms of the distance between the 2 points in question, then what you get is something that you know a priori is polynomially bounded times something that's exponentially small plus something, again, that's exponentially small times polynomially bounded. And that is exponentially small. Okay, so the idea is to use positivity of the Lyapunov exponent to get exponential smallness of that, and there are various methods of obtaining that. And so I will close with that. Thank you very much.
Yeah. I mean, the Thouless formula seems to be a one-dimensional thing, or
Yes.
what about higher dimensional?
Well, I mean, so the Lyapunov exponent as it's defined here is a one-dimensional thing because it uses transfer matrices. I mean, sure, I mean, you can always sort of look at directional Lyapunov exponents capturing growth of, well, you could try. Some people do that, but okay, so no, there's no higher dimensional analog of that formula.
We need a small break if nothing else because they need to set up the computer.